Hello. Okay, so now we're going to start chapter 16 on acid and base. Okay, acid and base are very important topics, particularly for those of you who go into the health science, and also for those of you who study biological science later on. Acid and base is a very crucial topics because everything that work in the bodies, in plants, in animals, basically in living organisms, the hydrogen ion concentration has to be proper in order for life to exist. Okay, and there's at least two parts to this chapter. There's part one. In part one, we're just going to do some review of basic concepts. And this part in itself is probably worth the whole chapter. And the reason I'm doing this is because the acid base traditionally has been a troublesome topic for many students. And now for the part one, I cover probably about 70 or 80% of that already in Chem 400. Okay, so if you were my student in Chem 400 before, you may have seen many of these slides. However, there are a number of slides that are new. And the reason I want to go over and cover this basic concept, because I don't know the backgrounds of all the students in the class. There were a number of students who may have taken the Chem 400 or the equivalents probably many years ago, so therefore you may not remember much. And depending on when you take, where you take the Chem 400 and the equivalent, your individual teacher may or may not cover some of the material in acid and bases. And then so the material I'm going to be talking about, in part one, review of basic concepts, it's going to lay the foundation, and it's absolutely necessary that you understand this. And so we want to do a review together so that everybody's going to start out on the same basis. Okay, and then so it's a very extensive review, and that's because in the past when I did review this acid-base concept, many students end up not doing well on this chapter. And in fact, acid-base concept not only cover chapter 16, but it also cover the first part of chapter 17. Which we continue with titration and buffers. Okay, so therefore I decide to spend some time to review the acid-base concept. Even though some of you may have learned in the Chem 1A or Chem 400 before, you are responsible for it. For this chapter, this review concept. Okay, there are three definitions of acid and base. The Arrhenius definition is probably the oldest and the simplest, so we'll review that Arrhenius definitions, and then we'll talk about the Brothes-Lowry definition of acid and base. And again, the Brothes-Lowry definition, I have discussed that in Chem 400. Okay, and then in part 2 we're going to discuss the last definition of acid and base is the Lewis definition, which is the broadest definition of acid and base. Okay, so let's go ahead and jump right into it. I'm adding a few more slides in the review, and then so compared to what I have put on Canvas, so maybe I can upload it at the new version of the review of the part 1 of chapter 16. Okay, so you can have some of the latest slides. But anyway, you should watch the lecture video, because sometime in the lecture video I have calculations and I add a few extra slides at the last minute in my explanation, and that may not be found in the version that I post on Canvas. Okay. And the first one is the Arrhenius concept of acid and base, and that's probably the oldest one and the simplest one. Okay, and it's back in 1884. There's a Swedish chemist by the name of Svante Arrhenius proposes the classification of acid and base. And so according to Arrhenius' classification, An acid is a substance that when dissolved in water increase the concentration of hydrogen ion in the solution. So for example, hydrochloric acid, in solution it dissolves to produce hydrogen ions, so it dissociates to produce hydrogen ions, so therefore it is an acid. And here's some of the common everyday life substances that household substances that are classified as acid. And acid tend to give you a sour taste, okay, because of the presence of hydrogen ions. And a base is, according to Arrhenius' definition, is a substance that when dissolved in water increase the concentration of hydroxide ion in the solution. And for example, potassium hydroxide, when it dissolves in water, it dissociates into hydroxide ions, and because of that, it is a base. Okay, and the base tend to give you a bitter taste, and also it feels slippery, just like soap. So if you pour some base on some weak bases on your skin, it feels very slippery, just like a soap. And here are some of the common household, everyday life stuff that are basic. You can recognize acid because it's usually the formula has the hydrogen ions, the acidic proton, because an acid produces hydrogen ions. So you can see that all of this has hydrogen ion beginning. Of the formula, there's one exception is the acetic acid. In the old ways of writing it, the acidic proton is this one right here, but nowadays it's written more in this formula here. And there's monoprotic and polyprotic acid. Polyprotic acid contains 2 or more ionizable hydrogen ions. And for a polyprotic, for example, phosphoric acid, which is a triprotic acid, it can ionize or release up to 3 protons into the solution. Usually the ionization of a polyprotic acid takes place stepwise. So for example, the first step is the release of the first hydrogen ions, and usually that's the most important, and it occurs at the highest dissociation percentage. And the second step is that these anions here, it undergo another ionization to give you another hydrogen ions. And then you can have and this one here, the anions can also undergo another ionization. So usually the latest step, in this case the step 2, step 3, it doesn't dissociate very much at all. So the hydrogen ions contribution from the step 2, step 3 is can be negligible, and only the first one is important. So, okay, now because the acid produces hydrogen ions in solution, okay, the hydrogen ions nowadays, people realize that it's not really a free hydrogen ions floating in an aqueous solution where there's water around. And that's because the water is polar, and water has long pair of electrons which are negatively charged, and the hydrogen ions produced from the acid are positively charged, so that hydrogen ions attract toward the oxygen where there's 2 long pair of electrons. So there's no such thing as a free hydrogen ions floating in solution, but rather the hydrogen attached to one of the water molecule to form a so-called polyatomic ions, and the name of that is hydronium ions. You may remember that in chapter 3 when we talk about nomenclature, okay, and there's a table of polyatomic ions. Most of the polyatomic ions are negatively charged, except for 2 that I mentioned. One is the ammonium ions, and the other one is the hydronium ions. Okay, so basically a hydronium ions is just a proton or hydrogen ions. And then but today people realize that the hydrogen ions in solution doesn't exist as a free hydrogen ions, but it's rather it combined with a water molecule to form hydronium ions. So in the old days, you can write the dissociation of hydrochloric acid this way. Just a single molecule of hydrochloric acid dissociated to give you hydrogen ions and chloride ions. But nowadays, you also write with the water, and because the hydrogen ion, when it dissociates, it coupled to the water to form hydronium ions. Okay, but anyway, it doesn't matter whether it's hydronium ions or hydrogen ions written like this, it's still hydrogen ion. It doesn't affect the property of this acid at all. Okay, so, but it's written, most today chemistry textbook written this way because it's a more realistic depiction of what the hydrogen ions looks like in the solution, in water. Okay. Okay, so now that we know how to recognize the acid formula, and there's different type of acid, monoprotic and polyprotic acid, how do you name acid? And there's two kinds of acid, binary acid. Binary means that you have two different type of element. For example, HF, HCl, so two different type of element in a compound. So that's called a binary acid. Okay, and then so there's for binary acid, there's two ways of naming it. You name them according to their anhydrous name, which means that this acid here can exist as a gas or a chemical compound. Okay, so as a gas or a chemical compound, they don't have any water associated with them. Okay, as a gas, there's no water associated, so that's why anhydrous. An means that without hydrous, water. So anhydrous. So they name as just like any other naming of any other covalent compound. So which means that you have two nonmetal, and the first nonmetal you use the elemental name given to it. So that would be hydrogen. And then the second non-metal, you name it using the stand name, so that's fluorine, so that's fluor, and ending in IDE. So, okay, ending in IDE, so that's hydrogen fluoride, hydrogen chloride, hydrogen bromide, etc. Okay, and this is hydrogen cyanide. Now this is not binary, this is actually three different elements, not just two. But the CN are treated as if it were a single entity. Okay. Now when this acid dissolve in water, then then you write it as aqueous, aqueous form. So you write that with a AQ after that. Okay, with a parenthesis AQ, which means after they dissolve in water. After they dissolve in water, then they can release that hydrogen ion to the water solution, and that's when they act as an acid. And then so they are named differently. So the naming when they dissolve in water is you name with the prefix hydro. Prefix means that the term that comes before. Hydro means water, and then you use a stand name. So for example, chlorine, the stand name is chlor. Okay, and then the suffix, it means that the term that comes after, the suffix is ic plus acid. So hydrochloric acid, hydrobromic acid, hydroiodic acid. Okay, and so that's the naming binary acid. And the other type of acid is the oxy acid. Oxy acid are acid that consists of a polyatomic ions. Okay, and then we learned about many of these polyatomic ions already before, like nitrate, sulfate, sulfide, phosphate, perchlorate, chlorate, chloride, etc. Carbonate. Okay, so we have learned about those polyatomic ions. Now when they couple with a hydrogen ions, for example nitrate, and when you put a hydrogen ions to it, so it becomes HNO3, because the hydrogen ion is positively charged and the nitrate has a minus charge. So when they come together, they form a neutral compound. Okay, and then so become nitric acid. Okay, and then you have nitrite ions when it's the acid form and become nitrous acid. Okay, so this polyatomic ion, it can couple with one or more hydrogen ions depending on how many negative charge it has. If it has one negative charge, then it coupled with just one hydrogen ions. And you notice here that the 8th ion, it becomes the ic acid, and the ITE ion become nitrous acid, OUS. Okay, so for example, sulfate has two negative charge, so it can take up to two hydrogen ions to become a neutral compound. So sulfate becomes sulfuric acid. So H2SO4. Okay, so two hydrogen ions. Again, you notice that the 8th ion become the ic acid and the 8th ion become the us acid. Okay, so that's the only guideline I can give you about this polyatomic or about this oxy acid. Okay, so you just have to memorize some of these acids. So these are the common ones. There's many more, but these are some of the most common ones that you're likely to encounter in the general chemistry class. Now, the naming of bases. Bases usually contain hydroxide according to Arrhenius definition. And then so you can have most bases are formed from group 1A and 2A metal. Okay, so for example, lithium hydroxide, sodium, potassium. So lithium, sodium, potassium are group 1A. These are the sodium and potassium are the most common one that you encounter in a chemistry laboratory. Lithium hydroxide is not very common and because very expensive. And then if you go down to group 1A, there is cesium hydroxide and francium hydroxide also. Okay, so all the group 1A metal. Okay, and so they are, and then you can also have the group 2A metal like calcium hydroxide, aluminum hydroxide. Now calcium has a 2+ charge and hydroxide has a -1, so therefore each calcium can combine with 2 hydroxide. Aluminum has 3+ charge, so it can combine up to 3 hydroxide, okay, to form a compound. So anyway, those compounds that contain hydroxide, you recognize it is a base because a base produces hydroxide when it is dissolved in solution. Now, there is some bases do not carry hydroxide. For example, ammonia. Ammonia is a base. It doesn't carry hydroxide. However, ammonia is a gas, but when it dissolves in water, okay, it can grab a proton from water and put it here because ammonia has a lone pair of electrons on the nitrogen, so it can form so-called ammonium ions. And when water loses the hydrogen ions, what's left is the hydroxide. And because this reaction produces hydroxide ions, when ammonia dissolves in water, it qualifies as a base because by definition, by the Arrhenius definition, a base is a substance that produces hydroxide. Okay, and some of the amine compounds are derived from ammonia. So if you replace the hydrogen ion with a methyl group, become methylamine, and then again in solution they also produce hydroxide, and because of that they are base compound. Let me put some of these on the whiteboard and I can go over that with you. Okay, so here's the ammonia. This is a Lewis structure of ammonia, and you may and then here it has a lone pair of electrons. Okay, so when ammonia dissolves in water, okay, and you know water is polar because oxygen is more electronegative than hydrogen. We'll talk about electronegativity in one of the later chapters. And then so this bond here is polar, the OH bond is polar, so that makes the hydrogen has a partial positive charge on it. The delta sign here indicates the partial charge. It's not a full-fledged positive charge, but only a partial positive charge because this bond is polar, and the oxygen has a partial negative charge. So therefore this bond, because this bond is polar, the hydrogen is held only very weakly by the oxygen, so it can be abstracted by a lone pair of electrons on the nitrogen because electrons are negatively charged. So the water can release a proton to the solution, okay, and then that proton coupled with the nitrogen to form a so-called ammonium ions. And now you don't release a neutral hydrogen atom, but it's actually a hydrogen ions. So therefore, when ammonia receives that hydrogen ions, it has a +1 charge. And then the water losing that hydrogen ions now become the hydroxide ions. Okay, so ammonia is a gas, but when the gas dissolves in the water, then you write it aqueous. And then some of the ammonia in the water, it can react with the water by grabbing a proton from the water to form ammonium ions. Okay? And because it produces hydroxide in solution, it qualifies as a base even though ammonia itself doesn't carry hydroxide ions. Now, if you replace one of these hydrogen, okay, so you replace one of this with a CH3 group, and this carbon attached to this nitrogen, okay, this group here, you can write it as CH3 like this, okay, and then it's called a methyl group. Okay, so you replace that, so now it becomes methylamine. Any compound that derives from ammonia, okay, that has ammonia, so it replaces the hydrogen with some other group. It can be methyl group, it can be a bigger group, doesn't matter. It becomes an amine compound. So amine compounds derive from ammonia. So here you have one methyl group, so you call that methylamine. And this is the expanded structural formula, but usually it's written like this, okay, as a condensed formula. And normally, so now the ammonia has a lone pair of electrons on it. Usually when it's written in condensed form, you don't put the lone pair of electrons. It's understood that it's there. Okay, so again, methylamine, when it dissolves in water, just like ammonia, because it has a lone pair of electrons, it can grab a proton from the water, okay, to form a so-called methylammonium ions. Okay, so you notice here that ammonia form ammonium ions, methylamine form methylammonium ions. Okay, and then again, because the water loses the proton, it becomes hydroxide. So therefore, methylamine in solution, it acts as a base. It will cause the solution to become basic because it produces hydroxide ions. Okay. Now what happens if we replace the other hydrogen also with some group like another methyl group? Okay. So let me just write it down for you. Okay. So here. This is if you replace two hydrogen with two methyl group, okay, so it becomes dimethyl, di means two methyl group, dimethylamine, and this is the expanded structure, and usually is written in this way as a condensed structural formula, okay, and then usually that lone pair of electron on the nitrogen is understood to be there. It's usually not written or indicated, but you have to know that it's there. So again, because it has that lone pair of electrons, it can abstract a hydrogen ion from water. So if you take dimethylamine and then you dissolve in water, it becomes aqueous. Again, aqueous because it has water as a solvent. So in the water, it can react with the water like this to form a so-called dimethylammonium ions. And because it produces hydroxide, so it qualifies as a base. Dimethylamine acts as a base in water solution. And if you replace the last hydrogen on ammonia with another methyl group, okay, so it becomes and again, this is a condensed structural formula. So it's written with a 3 methyl group, so you write CH3 in parentheses. And with a 3 here to indicate that there's 3 methyl group, and it understood that it's not the hydrogen that attached to the nitrogen, it is the carbon that attached to the nitrogen. Okay, and again, it does have that lone pair of electron in trimethylamine, and because of that, trimethylamine also acts as a base, and the acidic form is called trimethylammonium ions. Okay, now when you get to this stage here, you can see that the nitrogen no longer has a lone pair of electrons, so therefore it can no longer abstract a proton. So this species here, it cannot act as a base at all in solution, because so it cannot abstract a proton, and in fact it already have a positive charge on it, so it cannot attract another positive hydrogen ions to it, right? Okay, so that's so study this. So ammonia, methylamine, dimethyl, and then trimethylamine. So any compound again that is derived from ammonia are called the amine compounds. So they are called amine derivatives, and then so they all act as a base in solution as long as the nitrogen has a lone pair of electrons. You notice that whenever the nitrogen has 3 bonds around it, 1, 2, 3, okay, 1, 2, 3, then it always has that lone pair of electrons. So in solution it always acts as a base, because that lone pair of electrons allow it to abstract a proton from the water and thereby producing hydroxide, and it qualifies as a base. But whenever the nitrogen has 4 pair of bonding electrons around it, it always has a positive charge associated with that. And when it doesn't have that lone pair of electron, only 4 bonding pair of electron, then it no longer acts as a base. In fact, it acts as an acid. Okay, so here you have ammonia. In solution, it acts as a base because it grabs a proton from the water and it produces hydroxide, and because of that it acts as a base. Now ammonium ions, okay, in solution by itself, for example, if you take ammonium chloride, which is a salt, a solid, and you drop into water, and it dissolves in the water, and then you stir it up, everything goes in solution. So when it dissolves in water, we can write NH4Cl aqueous. But when it dissolves in the water, it dissociates into ions, so into the cations and the anions. The cations happen to be a polyatomic cations, NH4+. Okay, and most of the polyatomic ions that we learned, like nitrate, carbonate, sulfate, phosphate, they're all negatively charged. There's only a couple polyatomic ions that are positively charged. One of that is the ammonium ions. The other one is the hydronium ions that we talked about already. Only those two are positively charged. Now, when ammonium chloride dissolves in solution in water, it forms a solution of ammonium chloride, and it dissociates to give you ions. Now, the ammonium ions, it can release that proton, okay, it can release that to the solution, and then so it acts as an acid in this case, and then so when it releases proton, it becomes ammonia, and it forms hydronium ions. Okay, so therefore a solution that has ammonium that has ammonium ions in there is going to be acidic instead. Okay, and now a solution that has ammonia, then it's going to be basic because it has hydroxide ions. And okay, so now where do you get the ammonium ion? You cannot have a compound that has a positive charge. It always comes as a neutral compound. So usually it comes as ammonium chloride, whereas the chloride is a negatively charged ions that balance out this charge, the positive charge, but when you dissolve in water, it produces ions. And the ammonium ions, it will release the proton. Okay, some of it will release a proton to the water, so, and because of that, it causes the solution to be slightly acidic, and so it acts as an acid instead. Okay, and not a base. So ammonia is a base. So don't confuse between those two, ammonium ions and ammonia. They have different characteristics in solution. Okay, now there's strong acid and there's weak acid. Okay, strong acid dissociate completely or 100% in solution. For example, hydrochloric acid is a strong acid. In solution, it dissociates completely, so you write with a one-way arrow. It means that there's no HCl undissociated molecule in solution. everything dissociates to form ions in solution. Okay, so strong acid, you write with the one-way arrow in the dissociation of the hydrogen ions from the acid compounds. Okay, whereas weak acid dissociate less than 100%. Most weak acid dissociate somewhere between 0 to 5% only. And then so a majority of them, 95% or more, remain undissociated. And then for weak acid, for example, carbonic acid is a weak acid. So you write with a two-way arrow. Sometimes you can use the forward arrow. Forward arrow means that the acid dissociates, it releases a proton to the water, and the water receives that proton, it forms hydronium ions. And after carbonic acid loses that first proton, it becomes the hydrogen carbonate or bicarbonate, which is a common name. And then so initially, if you have 100% carbonic acid, okay, and then you got none of this, and then so therefore the forward reaction is going to go, it's going to produce ions. But as the ions product accumulated, they will start to react with one another, and they go back the other way, and then so therefore to reform the acid and the water. And at equilibrium, which means that the forward reaction and the reverse reaction come to a equilibrium, which means that they kind of equal one another. Okay, so then the forward rate of formation of the ions and the reverse rate of formation of ions equal one another. Then when you measure the concentration of the undissociated acid and the dissociated acid, usually more than 95% remain undissociated, only about 1 to 5% dissociate for weak acid. Sometimes to indicate the fact that more of the reactants are present compared to the product, you can use the reverse arrow, you draw with a bigger arrow, and then the forward arrow is smaller to indicate that only a small amount actually dissociated. Okay, so at equilibrium means that the steady state concentration of the reactant and the products no longer change. Okay, they achieve an equilibrium, so there's going to be more of the undissociated acid. So for weak acid dissociation, you write with a two-way arrow. You don't have to use the two arrow of unequal size. You can just use equal size, but you have to write with a two-way. Whereas for the strong acid, it dissociates 100%, so which means there's none of this at all. There's no equilibrium forming because the chloride and the hydrogen ions here, they will not combine and go back the other way at all. Okay, so they only dissociate 100%. Okay. I just showed here another example. Here, let me just turn on this light here, get a little bit more light in here. Okay, so this is another example of a strong acid, nitric acid. It's a monoprotic acid. It has only a single proton. So when you dissociate, it produces nitrate ion and hydrogen or hydronium ions in this case, 100% dissociation. Okay, so which means that it's not equilibrium. Okay, so which means that if you have, let's say you have 100 particles of nitric acid, when they dissociate, okay, you have 100 particles of this and 100 particles of the 100 particles of the hydrogen ions. Now remember, hydrogen ions exist in water as hydronium ions, but it's the same thing as hydrogen ions. Okay, so there's no more undissociated molecule of nitric acid around. Everything dissociates 100%. And this is written with a one-way arrow. Okay, whereas acetic acid is a weak acid. Acetic acid is found in vinegar. Okay, and so usually weak acid dissociate less than 100%, usually between 0 to 5%. Okay, dissociated. Acetic acid in vinegar at room temperature, acetic acid only about 1 to 2% dissociated, very low. Most remain undissociated. Only a tiny amount dissociated to give you the ions, acetate ions. Okay, so again, for weak acid dissociation, you write with a two-way arrow, so they reach a certain equilibrium. And at equilibrium, the forward rate of reaction equal the reverse rate of the reaction is still going full speed, but the steady state concentration no longer change because the concentration of, and then when they measure at equilibrium, there's a lot more undissociated acid than the dissociated form. Okay, and so therefore you have mostly molecules and only few ions. Whereas for the strong acid, you don't have any molecule at all, you have only ions. Okay, and so that's another example of a strong and weak acid dissociation. Okay, we also have strong and weak bases. And strong base are just like strong acid, it dissociates 100%. Most of them are the group 1A metal hydroxide. Okay, group 1A hydroxide, for example, sodium hydroxide, potassium hydroxide, because sodium, potassium, lithium, rubidium, cesium, all of those are the group 1A metal. They all form 1+ ions. And then so they only couple with one of the hydroxide because the hydroxide is a negative, has 1- charge. So again, if you have, let's say, 100 particles of sodium hydroxide in solution, none of them remain together. They will all dissociate to give you ions. Okay, you're going to have 100 particles of sodium and 100 particles of hydroxide if you start with 100 particles of sodium hydroxide. Okay, so again, you write with a one-way arrow. Okay, so that's a group 1A hydroxide, they all strong base, they dissociate 100%. Now the group 2A hydroxide are also strong, many of them are strong base. Okay, so example are barium hydroxide, strontium hydroxide. Now the group 2A metal, like barium, strontium, calcium, they have, all of them have a 2+ charge. And because of that, they couple with 2 hydroxide because each hydroxide is a negative. So therefore, when they dissociate completely, they produce 2 hydroxide ions. Okay, now they are not as soluble in solution as the group 1A. When the group 1A is a lot of them, I mean, you can take a handful like 300 grams per liter of water at room temperature, for example. You can dump a lot of that in solution. Now 300 grams, I just made it up. I don't remember exactly. Now different compound has different solubility, but which means that you can take a very large handful, drop into 1 liter of water at room temperature, stir it up, they go in solution. Whereas the group 2A hydroxide is not as soluble. If they only a tiniest amount, a small amount dissolve in water. Okay, but once they dissolve in the water, whatever soluble in water, they dissociate 100%. So again, that's why you write with a one-way arrow. And by definition, anything dissociate 100% is a strong base or strong acid. In this case, it's a strong base. Okay, so even though they're not as soluble, but they are considered also as a strong base because they dissociate 100% in solution. You will see that there will be compounds that are soluble, very soluble, but then when they go in solution, they don't dissociate very much at all. So they are not very strong electrolyte. Electrolyte are substances that produce ions like this. When they dissociate, they produce ion in solution. So they call strong electrolyte. So there are substances that are very soluble, but they don't produce electrolyte. They remain undissociated. Okay, so they are weak electrolytes. Okay, and so again, the definition of a strong acid, strong base is that they dissociate 100%. Now that has nothing to do with their solubility, which means that how much they can dissolve in water. Group 1A hydroxide dissolve a lot, whereas a group 2A metal hydroxide are not too very soluble, but because they dissociate 100%, they are also considered strong base. Now, but because of their less solubility, some chemists don't consider them as strong base. Okay, so for example, for barium hydroxide, or you have for some people, barium hydroxide, even though it dissociates 100%, but because only a small amount dissolve in water, so the amount of hydroxide produced is also small. So therefore, some chemists or some scientists consider that as a weak base instead of the strong base. Okay, so if you read different textbooks, they give you different ideas. So anyway, we're going to make a list of a strong acid and strong base, and we're going to go by that list for our purpose. Okay, here I give you some specific solubility data. Group 1A metal, for example, sodium hydroxide. If you take some solid sodium hydroxide and you add into 1 liter of water, okay, and then so when it goes solid, go into solution, it becomes aqueous. So when it dissolves, and when sodium hydroxide dissolves, because it is a strong base, it dissociates 100% to form ions. Now, for sodium hydroxide, you can dissolve up to 1,000 grams in 1 liter of water at about 25 degrees Celsius. Now, for a group 2A metal hydroxide like calcium hydroxide, again, if you put that in 1 liter of water, okay, you will find that only about 2 grams or so dissolve at about 25 degrees Celsius, not a whole lot. But wherever go in solution to become aqueous calcium hydroxide, it dissociates 100%. So therefore, because the dissociation 100%, so we write with a one-way arrow, and so therefore it's qualified as a strong base, because a strong base, like a strong acid, by definition, it dissociates 100%. However, for some chemists, they say that even though it dissociates 100%, but only about 2 grams dissolved in 1 liter of water compared to 1,000 grams over here. So a tiny amount that dissolved produces only a small amount of hydroxide. So they say that because it's not very soluble, it is a weak base instead. So there's some gray area in chemistry that's not always clear cut. Okay, and then so some chemistry textbooks consider calcium hydroxide, for example, as a strong base. Some others say no, it's a weak base. So anyway, I read several different chemistry textbooks and I kind of compile them together and come up with a list of a strong base and strong acid, so we can abide it by for our purpose, so that on the exam we're going to go by the same rules. Okay, now ammonia is a base because we learned that ammonia reacts with the water to form hydroxide ion in solution. Okay, so it's considered as a weak base, not a strong base, because the ammonia, only a small amount of ammonia actually reacts with the water. Most of it remains as unreactive ammonia in aqueous solution. Okay, so because of that, you write with a double arrow. So that's another example of a weak base, ammonia. Now, ammonia is a gas, and like any gas, either oxygen gas, nitrogen gas, any kind of gas, when it exposed to a body of water, some of the gas can seep into the water and dissolve in the water. And then so keep going in the water, and when the concentration get high enough, and some of that will come out of the solution, go back into the gas phase. So at some point it reaches an equilibrium. So I write with two-way arrow that equilibrium. Okay, so when it dissolves into the because gas can dissolve in water, that's why fishes can live under water, and then it still need oxygen, but the oxygen comes from the water. But the oxygen is the one that dissolve in the water. So the fish, they breathe through the gills, so they just swallow water, and then they push through the gill, and then the oxygen get absorbed in the gill into their blood system. Okay, so Anyway, so ammonia is a gas, so just like any gas, it will dissolve in the water, so become aqueous when it dissolves in the water. And then some of the dissolved ammonia react with the water to form hydroxide and ammonium ions. Only a small amount. Most of it remain unreacted. So probably less than 5% react. So just like any weak base. So because of that, ammonia is considered as a weak base. Okay. And by definition, a weak base only a small amount react with the water, and it's only to produce a small amount of hydroxide. It doesn't react with 100%. Okay, this slide shows the list of strong acid and strong base. Okay, so the strong acids, there are 6: hydrochloric, hydrobromic, hydroiodic, nitric perchloric, and sulfuric acid. Just about every general chemistry textbook nowadays lists these 6 acids as strong acid. Now there are many more strong acids, but in general chemistry, we're limited to these here, and they are the most common one. Now, if you go on to organic chemistry, you probably will encounter other type of organic acid that are strong also. But this is it. So if you know the list of the 6 strong acids, any other acid that doesn't belong on the list of 6 strong acids is going to be considered as the weak acid. Okay, so for example, phosphoric acid, carbonic acid, acidic, hydrofluoric acid, etc. These are all considered weak acid. How come? Because they're not on the list of 6 strong acids. But anyway, the 6 strong acids, they dissociate 100% in solution. Whereas the weak acid or weak electrolytes, they only dissociate partially, maybe up to about 5% or so in solution. Okay, sulfuric acid is strong. Sulfuric acid is the diprotic acid. Okay, it has up to 2 protons, but only the first proton is considered as a strong acid. So it releases 100%, the first hydrogen in solution. The second hydrogen is not considered as a strong acid. But anyway, we don't have to worry about this for now. If you go on and take Chem 401, then we'll come back to this one. Okay, so again, so let's just consider as a strong acid, both hydrogen ions, okay, for our purpose here. Okay, and these are the list of the strong base. So all the hydroxide of group 1A metals, like lithium, sodium, potassium, rubidium, etc. Those are strong. Okay, so sodium hydroxide, potassium hydroxide are most commonly used in the general chemistry lab in the college. Lithium hydroxide, cesium, rubidium hydroxide, you don't see them very often because I think they're rare and they're a lot more expensive. So most of the time you're going to see sodium or potassium hydroxide. And for the group 2A metal, we're going to consider the calcium, strontium, and barium hydroxide as strong base only. Okay, so and other things like magnesium hydroxide. Okay, so we're not going to consider as a strong base. Okay, so these 3 are the strong bases. So which means that they dissociate 100% in solution. Okay, and weak bases are either ammonia or derivative of ammonia, which we talked already about, and they're called amine compounds. So you can replace the hydrogen on the ammonia by another groups. Okay, so R prime or R2 prime are just different groups attached to the nitrogen. But as long as the nitrogen still have that lone pair of electron, it does act as a base, as we have discussed. Okay, so just make sure you know the list of the strong acid, and these are the strong base. So everything outside of that is going to be weak acid and weak bases. Okay, strong acid, strong base, neutralization reactions. When you put a strong acid and you mix that with a strong base, what you have is that the strong acid dissociates to produce hydrogen ions, and the strong base dissociate to produce hydroxide ions. When you put a hydrogen and hydroxide ions together, they will come together instantly to form water. Okay, so water is come from the combination of hydrogen ions and hydroxide to form water, and what's left behind is a sodium and the chloride ions. So sodium and the chloride together, so it forms a salt. So a strong acid and a strong base, or any acid and base, when you mix them together, you're going to end up with water and a salt. Okay, and then so now remember that the salt here, that's a strong electrolyte, and anything that has sodium ion is going to be totally soluble. We talked about the solubility guideline back in chapter 3. And then, so this is aqueous, and this is aqueous, a strong acid and strong base, and water, the physical label is liquid. Okay, now, so here you have a acid and a base. So this is a monoprotic acid, and the base only produces a single hydroxide. Okay, if you use a base that has 2 hydroxide, like barium hydroxide, so this is a strong base also. So therefore, because it has 2 hydroxide, you need to use a 2 right here, put a coefficient 2 in front of the hydrochloric acid formula in order to produce 2 hydrogen ions, which react with 2 hydroxide to give you 2 water. Okay, and the barium has a 2+ charge. It balanced out by the 2 chloride. So you write that barium chloride. Okay, so again you got an acid and a base. You're going to have a salt, which is this one right here. A salt, remember, that's a generic term for ionic compounds. And then you have water. Okay, so let's do some acid-base writing a balanced equation and net ionic equations. Okay, so for this reaction here, write a balanced molecular equation and a balanced net ionic equation. So here you have sulfuric acid, cesium hydroxide, that's a strong acid, strong base. Nitric acid, that's a strong acid, and this is strong base. Okay, and barium hydroxide, that's a strong base and a strong acid. Okay, let me do A and B for you, and then show you how to do that, and then you can go ahead and do C for yourself. Okay, so on the next slide it shows, okay, so A right here, sulfuric plus cesium hydroxide. Okay, so what is the product? Write a balanced molecular equation and a net ionic equation. Now sulfuric acid is a strong acid, and it's a diprotic acid, so it can produce up to 2 hydrogen. Okay, 2 hydrogen, and then you have a sulfate. Okay, so if the sulfuric acid dissociates completely, so it's going to produce 2 hydrogen and sulfate ions, and the cesium hydroxide produce a cesium ions and hydroxide ions. Now we got 2 hydrogen ions here, so we need 2 hydroxide, so therefore we need to put a 2 right here. So that's what I do, I put 2 right here in order to produce 2 hydroxide, and then you also have 2 cesium. So again, you have, when you write the molecular equation, Me stands for molecular equation, you have to balance it. So the 2 hydrogen ions produced by sulfuric acid react with the 2 hydroxide to produce 2 water. What's left is that you got 2 cesium. Cesium is a +1 charge, is a group 1A metal. Okay, and then you got the sulfate. Sulfate has a 2- charge, and then you need to balance that with a 2 cesium. So you put that together as a cesium sulfate. Okay, but anyway, cesium sulfate is soluble, so you write that with aqueous and then water. Okay, so now that's the molecular equation. For net ionic equation, you need to cancel out all the spectator ions, right? And then so from this here, you break it down, the strong acid to 2 hydrogen and sulfate, and this produce 2 cesium and 2 hydroxide here because aqueous, so you got 2 cesium here, and the sulfates right here. Okay, and then 2 water. Now water is a liquid, and it's a molecule. Okay, water, it doesn't break apart into hydrogen ions and hydroxide. Anyway, it does dissociate a tiny teeny amount into hydrogen ions and hydroxide, but mostly it just remains undissociated. So therefore, we cannot break it down into ions. Okay, so we have to leave it like this. So therefore, if you cancel out the common ionic species on both sides of the equation, then you cancel out the sulfate right here. Okay, so the sulfate is still ions on both sides of the equation, so nothing happened to it. The 2 cesium also, you canceled it out. So what left is the 2 hydrogen react with the 2 hydroxide right here to give you 2 water. Okay, so that will be your net ionic equation. Okay, now I rewrite this equation because you have to, in a balanced equation, you have to express the stoichiometric coefficient in the lowest common denominator. So you divide this by 2, and then so this is the proper way to express that. So basically the net ionic equation for a reaction between a strong acid and a strong base is just the formation of water. Okay, and so here's, let's go on to B. This is strong acid and strong base, nitric acid and calcium hydroxide. Notice that the calcium hydroxide has 2 hydroxide ions, whereas the nitric acid is only monoprotic acid. Okay, so strong acid produces hydrogen ions and the nitrate ions, and strong base produce calcium and 2 hydroxides. So again, you got 2 hydroxide, you need to put a 2 in front of the nitric acid to balance it because you need 2 hydrogen ions. So for the molecular equation, I put 2 right here. 2 nitric acid react with the calcium hydroxide, and the 2 hydrogen ions react with the 2 hydroxide to give you 2 water. And what's left is that you got the calcium, which has a 2+ charge, and the nitrate ions. Okay, you need to recognize this is a polyatomic nitrate ion, which has a -1 charge. So therefore, the formula for calcium nitrate is 1 calcium and 2 nitrate. But it's aqueous because anything that has nitrate is totally soluble. So therefore, in solution, they exist as ions. So if you break this equation down into ions, then you got 2 hydrogen ions, 2 nitrate, you got calcium and 2 hydroxide. Here you got calcium and 2 nitrate here. And again, water, you have to leave it as it is. You cannot break it down into ions. Okay, so therefore you cancel out the spectator ions, the nitrate, calcium, here's the calcium nitrate. And what's left behind is again, you got the hydrogen ions plus hydroxide to give you water. So you can see that the net ionic equation for this reaction is identical to this one. So basically when you have a strong acid and a strong base mixed together in equal amount, in equimolar amount, same molar amount, you're going to end up with a formation of the water as a net ionic equation. Okay, let's see. Okay, many of the metal hydroxide are very insoluble. So if you go back and consult the solubility table, most of the substance that has hydroxide in there are not very soluble unless the hydroxide coupled with ammonium ions and the group 1A metal. Okay, so all of these here, mercury 2, chromium, aluminum, iron, they're not part of the exception. So any of these compounds here, these metal hydroxide are very insoluble. They don't dissolve in water readily at all, and if they do, only a teeny amount dissolve it. So you take a spoonful of that, put into the water and stir it up. Most of this is going to sit at the bottom as a solid, okay, and they only go into very sparingly into solution. So they are very insoluble, but they carry hydroxide. Okay, so what happens is that if you add an acid to it, so here you have a beaker that has water, and there's a whole bunch of this ferric hydroxide, which is insoluble, sitting at the bottom. But if you pour some acid into it and stir it around, okay, what happens is that the acid produces hydrogen ions, and the hydrogen ions is going to zoom right into the crystal, the solid crystal that are formed by the ferric hydroxide because they are ionic compounds and it's not soluble. So most ionic substance as a solid, it comes in as a crystal of solid, just like sodium chloride crystal. Okay, and then so the hydrogen ions from the acid is going to zoom right into it, and it recognizes the hydroxide and it reacts with hydroxide to form water. But by doing that, it pulls the hydroxide straight out of the crystal. So it caused the ferric ion to go right into the solution. So it solubilized the ferric hydroxide solid. Okay, so basically you can dissolve any of these compounds by acidifying the solution. by adding an acid to it. So you make it go in solution. If you add enough of that, you're going to make all of that go into solution. Okay, so again, you have to, when you write the formula for the reaction, you have to balance the equation. Each of these carry 3 hydroxides, so you need 3 hydrogen ions. So if you use hydrochloric acid, which is monoprotic acid, you need to put a 3 right here. Okay, to produce 3 hydrogen ions, react with the 3 hydroxide to give you 3 water. And the ferric ions has the 3+ charge, or Rn3, Roman numeral in parentheses, Rn3, and then it balances out by the 3 chloride, so you can write together like this. Now ferric chloride, based on the solubility guideline, is soluble, so you write that with aqueous. Okay, now this is the same thing. Here's aluminum hydroxide, not very soluble at all. And then so in the presence of an acid, so you can use any kind of acid. Okay, so here I chose to use a different acid, so nitric acid. Again, you need 3 protons to react with 3 hydroxide. Okay, to give you 3 water. Aluminum is a 3+ ions, and it balances out by the nitrate, because nitrate is a -1 charge, so you got 3 nitrate. Okay, so again, anything that has nitrate is soluble, so that's why you write that with the aqueous. Okay, again, let's write a balanced molecular equation and balanced net ion equation for the following acid-base reaction. So now this is an acid right here, perchloric acid, nitric acid, sulfuric acid, all those are strong acid. And the copper hydroxide, mercury 2 hydroxide, and chromium hydroxide, those are insoluble basic compound. So if you take this and add into water, it mostly is not soluble. 99% of that is insoluble. Maybe a tiny fraction actually go in solution, produce a tiny amount of hydroxide. Okay, so let me do A and B. Okay, to show you how to write the balanced molecular equation, and you can go ahead and do C yourself. Okay, so first one is copper hydroxide and perchloric acid. So it's right here. Now this is a solid. Okay, so therefore solid doesn't dissociate it. In solution, it doesn't break down, so you cannot break it out into ions. Perchloric acid is strong acid, so dissociate 100%. So therefore you can write it, break it out into hydrogen ions and perchloric ions. Now you notice that the copper hydroxide has 2 hydroxide ions, so you need 2 hydrogen ions. So therefore on the molecular equation you need to put a 2 right here. Okay, in order to produce 2 hydrogen ions, which react with the 2 hydroxide to form 2 water. And what's left is that you got the copper with a 2+ charge. Okay, because the hydroxide is a -1 charge, but you got 2 hydroxides, so therefore you know the copper has to be a 2+, which is balanced out by the perchlorate ion, ClO4, it has a -1 charge, so therefore you put a 2 right here, that's 2 perchlorate. So copper perchlorate, now anything that has perchlorate ion is totally soluble based on the solubility guidelines, so therefore you put an aqueous right here. Okay, so that's the balanced molecular equation. Now for the net ionic equation, you will cancel out all the spectator ions. So let's see what are the spectator ions. Now this is a solid, so you have to keep it as it is. Okay, so if it's a solid, if it's a water, liquid, and later on when you see a gases, you cannot break them down into ions. Or it's a weak electrolyte, you cannot break them down into ions. Okay, you have to keep them as they are, because the solid doesn't dissolve to form ions. So, but perchloric acid is a strong acid, produce 2 hydrogen ions and 2 perchloric ions. This is aqueous, so therefore in solution it produces copper ions and 2 perchloric ions from here. And then you got 2 water. So therefore the spectator ions are you can cancel out the 2 perchloric ions here, because you can see that on the left side and the right side equation is the same thing. It hasn't reacted at all. And you cannot cancel out the copper ions because the copper is tied up in the solid over here. Okay, so you can't do it. So it has to be the same nature on both sides before you can cancel it. And you cannot cancel out the hydrogen ions because there's no hydrogen. The hydrogen ion is tied up in the water on the right side. Okay, so therefore you can only cancel the perchloric ions. So the net ionic equation is the copper hydroxide react with the hydrogen ions to produce copper 2 plus and then 2 water. Okay, so basically the 2 proton zoom in and then it react with this, it pull it straight out and go into the water, and then the copper now when it lose the hydroxide is no longer in the solid state, it dissolve it go right into the solution, and then that's why you write copper 2 plus aqueous. So it's ion dissolved in solution. Okay, for the B right here, nitric acid and mercury 2 hydroxide. So this is nitric and mercury 2 hydroxide. So nitric is a strong acid, so produce a single hydrogen and the nitrate ions. Okay, now this is a solid, so you cannot break it out into ions at all. Now again, the mercury hydroxide has 2 hydroxides, so I need 2 protons. So therefore, in the molecular equation, I put a 2 right here. React with the mercury 2 hydroxide to give you, okay, the 2 hydroxide here. I mean the 2 proton here. It goes zoom right into it. React with the 2 hydroxide. It pulls straight out to form 2 water. And when that mercury hydroxide solid lose the hydroxide, it go right into solution. So it has a 2 plus charge, and it's balanced by the 2 nitrate ions from here. So you write with the mercury nitrate with a 2 in parentheses because you got 2 copy of the nitrate ions. And again, anything that has nitrate is totally soluble in solution, so that's why you write it aqueous. Okay, so that's for the balanced molecular equation. For the net ionic equation, you're going to cancel out the spectator ions. Again, the nitric acid break down into hydrogen ions and nitrate ions. This one is a solid, so you cannot break it out into ions. You have to keep it together. And over here, this is aqueous, so therefore you can write it break down into ions. Mercury 2 plus, and here you got the 2 nitrate ions. The water you have to keep as it is. So the only common chemical species on both sides that hasn't reacted is the nitrate ions here, so you can cancel that out. So therefore you're going to have the 2 plus hydrogen plus the mercury hydroxide solid plus the mercury 2 ions and water. Okay, again, very important when you write net ionic equation, make sure you put all these physical labels. Okay, aqueous, solid, liquid, etc. Okay, the next topic is the oxide of metal and non-metal and how they behave in solution. Oxide of metal. So let's look at oxide of metal. Oxide are compounds that have oxygen and it has non-metal. For example, CO2. CO2 is an oxide compound that has carbon, which is a non-metal, so we call that an oxide of non-metal, or sulfur trioxide. So it's an oxide compound because it has oxygen and it has sulfur, which is a non-metal, so oxide of non-metal. So these oxide of non-metal, when they dissolve in water or react with the water, they form acidic substance. For example, carbon dioxide. Carbon dioxide is a, that is a global warming gases. It's a man-made substance produced, and it also produced in nature. But a lot of things that come from human activity, for example, the burning of fossil fuel, car engine, and things like that, produce of carbon dioxide. And the carbon dioxide rises in the air. In the atmosphere, it can react with the moisture, with the water in the air, in the atmosphere to form carbonic acid. And carbonic acid is a weak acid. It dissociates to form hydrogen ions. Okay, so that's the example of an oxide of non-metal. When it dissolves in water or react with the water, it forms an acid solution. Okay, now CO2 is a gas, and like I mentioned before, any gas when they exposed to a body of water, it can dissolve in the water, and some of that can react with the water. Because of the rises in the CO2 gas in the atmosphere in recent decades, they found that the ocean water being a little bit more acidified. Okay, ponds and lakes also become more acidified because of the rise in the water, and acidification of the ocean water, it has an adverse effect on the biological organism, on wildlife, and on the some of the Great Rift Barrier in Australia also start dying off because of the acidification of seawater, and other environmental problems also. Here's another example of an oxide of non-metal, for example sulfur dioxide, which is a man-made byproduct. It came out of the industrial smokestack. Okay, this particular in the eastern province of Canada and the United States. They have a lot of this industrial smokestack and producing a lot of sulfur dioxide into the atmosphere. And then in the atmosphere, it can react with the oxygen, the sulfur dioxide, to form sulfur trioxide. And sulfur trioxide react with the moisture in the air, water in the air, to form sulfuric acid. Okay, so again, an oxide of non-metal are form acidic substance when they dissolve in solution. Another example is the nitrogen dioxide came out of the exhaust of the combustion engine. Again, so it can rise in the air and react with the moisture in the air to form nitric oxide and nitrous acid. Nitric acid and nitrous acid. So all of these acid here, nitric, nitrous acid, sulfuric acid, carbonic acid, due to these non-metal oxide gases, okay, produced. And then what happens is they come down with the rainwater and it acidifies the rainwater. It can cause a lot of environmental problems. In Europe, they have a lot of this marble status outdoor. It's made of calcium carbonate. And when the rainwater comes, the acid in the rainwater, it dissolves the calcium carbonate. Okay, so it can cause damage to it. Acidifying of the rainwater, it can decimate forests, cause trees to start dying, and ponds, to acidify, it can kill the local fish population. So it's a big environmental problem. So nowadays there is a federal mandate that all the industrial smokestack has to be fitted with a filter so that the sulfur dioxide that produced, most of it get removed before the exhaust are released into the atmosphere. Okay, so anyway, the point here is the oxide of non-metal, when they dissolve in water solution, it produces a acidic solution. Okay, now let's look at the oxide of metal. Oxide of metal, for example, oxide again are compounds that carry one or more oxygen, and metal, for example, calcium, magnesium, those are metal. So these, when they dissolve in the water, it produces hydroxide, so therefore it produces bases instead. So therefore you call the oxide of non-metal are basic oxide because they give a basic solution when they dissolve in water. And we know that calcium hydroxide, magnesium hydroxide are bases. So in solution, these can dissociate to give you hydroxide ions and calcium ions. And because it produces hydroxide ions, it acts as a base. Okay. Now magnesium hydroxide is used as an antacid. So sometimes you have stomach upset because you have too much acid produced, or due to a variety of reasons, anxiety, stuff like that, produce acid, and then so you take some of the Tums or some of these antacid, which basically magnesium hydroxide, which produce hydroxide, and it neutralizes all the hydrogen ions, from the acid stomach. Okay, so if I ask you, if you take dinitrogen pentoxide solid and then you dissolve in water, okay, so you take a handful of N2O5 compounds, drop into a beaker of water, stir it up, and when it goes solution, will the solution be acidic or basic? Okay, and then so now N2O5, this is an oxide of non-metal, right? Because nitrogen is a non-metal, so therefore, just like CO2 or sulfur dioxide or NO2 that we've seen, they will form a acidic solution. Okay, so it's going to be acidic instead. And what about P4O10? So this is tetraphosphorus pentoxide. Oh no, theta phosphorus dicoxide, deca. So that's 10 dicoxide. So when you dissolve that in water, will it form a acidic or basic? Again, this is an oxide of non-metal because phosphorus is a non-metal, so it's going to be acidic. Okay. And what about if you take potassium oxide, you dissolve in water? In this case here, you have an oxide of metal because potassium is a metal. So therefore, like sodium oxide or magnesium oxide that we seen before, so in solution they will form a basic solution. Okay, so it's going to be basic here. Solutions. Okay, so that's oxide of metal and oxide of non-metal behavior in water. So the next slide here show the second definition of acid and base. And this is called the Brontes-Lowry definition of acid and bases. And this definition came up by two independent scientists. One is the Johannes Bronsted in 1923 in Denmark, and the other one is Thomas Lowry from England. So together came to be known as the Brontes-Lowry definition of acid and base. And according to Brontes-Lowry definition, an acid is a substance that donates a proton to another substance. Okay, it donates a proton to another substance. So it's similar to Arrhenius' definition, right? Because an Arrhenius' definition of an acid is a substance that produces hydrogen ion when they dissolve in solution. And then, so therefore, if you produce ion, you are also a proton donor, right? Because the hydrogen ion is a proton donor and it's also known as a proton. Okay, so again, so here you have a hydrochloric acid, which is a Arrhenius acid because it produces hydrogen ion when it dissolves in aqueous solutions, and because it produces hydrogen ion is also a proton donor. So therefore, all Arrhenius acids are Brontes-Lowry acid by definition and vice versa. Now, Brontes-Lowry base is a substance that accepts a proton from another substance, and therefore, because it accepts another proton from another substance, it has to have a pair of electrons in order to accept it. Just like we saw in the case of ammonia, the nitrogen has a lone pair of electrons on it, so it can accept a proton from water. Okay, so anything that accepts a proton or a hydrogen ion, which is positively charged, it must have a lone pair of electrons in order to accept it. So, for example, ammonia here, there's a lone pair of electrons on the nitrogen. Okay, so you can grab a proton from the water to become ammonium ions, and then so it produces hydroxide. Because produced hydroxide, it is a Arrhenius base, because all Arrhenius base by definition produce hydroxide ions when they dissolve in water. And in this case here is also a Brontes-Lowry definition of a base because it's a proton acceptor. Okay, a Brontes-Lowry base is a substance that accepts a proton from another substance. So accept a proton, so therefore it qualifies as a Brontes-Lowry base. So you can see now in this example, a Arrhenius base like ammonia is also a Brontes-Lowry base. And the question is, are all Brontes-Lowry base or Arrhenius base? You know, the vice versa case, is that the same? Okay, let's look at some example. Let me write it on the board here. So first here, the Arrhenius definition of an acid. So let's just call that Arrhenius acid. It's a compound that produces hydrogen ions when dissolved in aqueous solution. Aqueous solution is water, in which water is a solvent. Okay, so it produces hydrogen ions. So that's the definition of Arrhenius acid. Brontes-Lowry definition of an acid is a substance that donates a proton. So therefore, it is a proton donor. And because Arrhenius acid produces hydrogen ions, so basically it releases hydrogen ion to the solution. So that's the same thing as a brontoslurry acid, which also release a proton to the solution. So therefore, we can say that an Arrhenius acid is a brontoslurry acid and vice versa. And all brontoslurry acid are also Arrhenius acid. Okay, and now let's look at the case of bases. Okay, now let's look at the example of Arrhenius base and brontoslurry base. Let's see, let me just underline it here. Okay, so an Arrhenius base is a substance that produces hydroxide ions when dissolved in water to form an aqueous solutions. Okay, so for example, sodium hydroxide in solution, it produces hydroxide ions, so that's an Arrhenius base. And ammonia react with the water because ammonia has a lone pair of electron here. You can grab a proton, it produces hydroxide, so it's an Arrhenius base. Now, those that produce hydroxide, they are hydroxide by definition because the hydroxide, it has this lone pair of electron. It can also grab a proton from water, okay, to form water, and in the process it produce hydroxide from this water here. Okay, so basically they just exchange hydrogen ions, and then so because of that, you know, any substance, any Arrhenius base produce hydroxide, and by definition hydroxide are also a proton acceptor because a brontoslurry base is defined as a hydrogen ions or a proton acceptor because I accept a proton, so therefore it is also a, so any Arrhenius base is also a brontoslurry base. Here's another example of brontoslurry base as a proton acceptor. Ammonia react with the water. Again, I draw with a lone pair of electrons on the nitrogen. It can grab a proton from the water to form ammonium ions and hydroxide. So in this reaction here, it is also a Arrhenius base, and because it produces hydroxide ions, but it also a brontoslurry base because it is a proton acceptor. So therefore, ammonia in this case here is both a brontoslurry base and a Arrhenius base. But in this case down here, the ammonia, when you react with the hydrochloric acid, so if you, instead of taking ammonia and put it into neutral water, it will react with the water. But if you put it into an acidic solution where there's a lot of hydrogen ions floating around, because remember hydrochloric acid is an acid, it produces hydrogen ions, right? And it dissociates to form hydrogen ion in solutions. So therefore the hydrogen ions will react with that lone pair of electron which is negatively charged to produce ammonium ions, and in the process it produces chloride ions. So in this reaction here, there's no hydroxide produced at all. So therefore, technically, it is not a Arrhenius base in this case right here, whereas ammonia up here, it is an Arrhenius base, but in this reaction, it does not act as an Arrhenius base. But it is a brontoslurry base because it is a proton acceptor. Okay, so now we can say that all brontoslurry base are Arrhenius base because all brontoslurry base produce hydroxide, and hydroxide has lone pair of electron. They can accept a proton. Okay, so any brontoslurry base must have at least one lone pair of electron to accept a proton because it's a proton acceptor. Okay, but in this example here, it doesn't produce hydroxide, so therefore this brontoslurry base in this particular reaction does not act as a Arrhenius base. So therefore the definition of a brontoslurry, the brontoslurry definition of acid base is a little bit broader than the definition of Arrhenius acid base. So not all brontoslurry base are Arrhenius base, but all Arrhenius base are brontoslurry bases. Okay, and this slide here, it shows the water in the presence of hydrochloric acid in solution. Because hydrochloric acid is a strong acid, it's much stronger than water. And if you draw the Lewis structure of water, water has two lone pair of electrons. Okay, so therefore it can use one lone pair to accept a proton from hydrochloric acid. So it is a proton acceptor, so therefore it acts as a Bronte-Lowry base in this case. Whereas in the case below here, water is a stronger acid than ammonia. And in this case here, it can donate a proton to that lone pair of electron on the nitrogen of ammonia. So in the case here, it acts as a Bronte-Lowry acid because it's a proton donor. Whereas here, the ammonia acts as a Bronte-Lowry base because it is a proton acceptor. Okay, so water, and there are several different species also, can act as a base in one case and a Bronte-Lowry acid in another case. And a substance that can act sometime as an acid, sometime as a base, by either donating a proton or accepting a proton from another substance is called an amphiprotic substance. Okay, we'll come back to that in a couple slides. Okay, conjugate acid-base pair. In any Bronte-Lowry acid-base reaction, there's always two conjugate acid-base pair. Okay, so let's look at this example here. Hydrofluoric acid is a weak acid. Notice here it's a weak acid because the reaction is written with two-way arrow. So in water, hydrochloric acid produces hydrogen ions, and the hydrogen ions react, it couple with the water to form hydronium ions. And when the hydrofluoric acid donates a proton to the water, it becomes the fluoride ions. So here's the acid. When it loses a proton, then it becomes the conjugate base. Okay. Now, a base is because the reverse reaction. Remember that a weak acid or a weak base, you write the reaction with a two-way arrow. So it goes this way and go back the other way also. So if you go back the other way, it accepts a proton from hydronium ions to reform hydrofluoric acid. Okay, so an acid, when it donates a proton to the solution, it becomes its conjugate base. And water in this case acts as a Bronte-Lowry base because it accepts a proton from hydrofluoric acid, okay, to form hydronium ions. So when a base gains a proton, it becomes the conjugate acid. And then again, if you go back the other way, then it donates a proton to fluoride ions to go back to become water. So in this case, it is an acid in the reverse reaction because it donates a proton. So therefore, any Bronte-Lowry acid-base reaction, there's two conjugated acid-base pair. This is the HF, and the F minus is the first conjugate acid-base pair, and the other one is a water and hydronium ions is a second conjugated acid-base pair. Okay, and between the acid and the conjugate base is the gain and loss of a hydrogen. You always look for the acid and the base on the left side of the equation, and the conjugate acid and the conjugate base always look for it on the right side of the equation. Okay, so that's the convention for Bronte-Lowry acid-base reactions. Okay, so let's look at this example here. Identify the Bronte-Lowry conjugate acid-base pair in each of the following reactions. Okay, ammonium ions react with the water to give you hydronium ions and ammonia. So which one is the acid and which one is the base? Which one is the conjugate acid and which one is the conjugate base? Okay, so an acid, a Bronte-Lowry acid is a proton donor. In this case here, ammonium ions donate a proton to the water. So therefore it's an acid. When it releases a proton to water, it becomes ammonia. So ammonia would be the conjugate base. And water accepts a proton from ammonium ions, so therefore water is a base. And when it accepts a proton, it becomes hydronium ions. So it is a conjugate acid. Okay, so here's the acid, conjugate base, conjugate acid. So that's 2 conjugate acid-base pair. Let's look at example B. Okay, hydrocyanic acid react with nitrite ions to give you nitrous acid and cyanide ions. So obviously HCN is an acid, it donates a proton to nitrite to become Cn minus. So therefore this is the acid and its conjugate base Cn minus or cyanide ions. And nitrite is a base which accepts a proton from hydrocyanic acid to become nitrous acid. So this is a base and this is the conjugated acid. Okay. Example C, you have carbonate ions react with the water to give you bicarbonate and hydroxide. In this case here, water is a proton donor. It donates a proton to carbonate ions. So therefore it's an acid, and when it loses that proton, it becomes hydroxide. So that's the conjugate base. And carbonate ion receive a proton from water, so that a Bronte-Lowry base. And then when it accepts that proton, it becomes hydrogen carbonate. So that will be the conjugate acid. Okay. Notice here that when it accepts a proton from the water, because proton has a positive charge, and carbonate ions has a 2 negative charge. So when they accept a proton, one of the negative charge is neutralized. So therefore the bicarbonate has only a -1 charge rather than -2 charge. Okay, and lastly you have this is the acetic acid. In water it dissociated just like any weak acid, right? Hydrocyanic acid, ammonium ions, those are all weak acid. So they dissociated in solution up to between 1 and 5% at about room temperature. Okay, so when it dissociates, it produces a proton right here, the acidic proton. It gives to water, it becomes the acetate ion. So this is the acid, it's conjugate base. This is a base, and that is conjugated acid. Okay, I mentioned about the amphiprotic substance. Okay, amphi means that it can go either way, and protic stands for proton, so which means a substance that can accept a proton or donate a proton. Okay, so for example, back here, okay, in this case here, water accepts a proton from HCl, so it acts as a Bronte-Lowry base. But here against ammonia is a stronger acid, so it can donate a proton to ammonia. So here it acts as a Bronte-Lowry acid. Here it acts as a Bronte-Lowry base. Okay, so a substance that can act sometimes as an acid and sometimes as a base by losing or gaining an electron. By losing or gaining a proton is called amphiprotic substance, because by donating or losing a proton, it can act as an acid or a base. So again, here's the example. I just here the water act as a proton acceptor. Here is act as a proton donor. Okay, and most of the amphiprotic substances are intermediates substance of a polyprotic acid. For example, hydrogen carbonate. Hydrogen carbonate came from carbonic acid, which has 2 protons. So when it releases a proton, it becomes hydrogen carbonate. And that hydrogen carbonate can act as an acid by donating another proton to the solution to become carbonate ions, or it can act as a base by accepting a proton from water or some other source in order to become a H2CO3. So it can either donate a proton or accept a proton. So it's called a amphiprotic substance. Okay. Okay. So here's carbonic acid. The hydrogen. I'm focusing on that hydrogen carbonate example for now. Carbonic acid in solution is a weak acid. It dissociates the first proton to give you hydrogen carbonate. Okay, and the hydrogen carbonate, it can act in 2 ways. It can go on and dissociate that second proton, so it produces another hydrogen ion. It just releases that into solution. so that's act as an acid, or the hydrogen carbonate can accept a proton from some source, for example from water, to produce carbonic acid again. So in this case it acts as a base. Okay, so hydrogen carbonate is an amphiprotic form. So an amphiprotic form are very commonly, they are intermediate form of the polyprotic acids. Let me just put some of the material on the whiteboard. Okay, so here let me just, so here's carbonic acid. Carbonic acid is a weak acid, so therefore the dissociation reaction is going to be written with a two-way arrow. Okay, and then so it produces hydrogen carbonate. Now hydrogen carbonate, there's two things that can undergo two the reaction. One is that it acts as a Bronte-Lowry acid by donating the second hydrogen ion, because this is a diprotic acid. It can donate the second hydrogen ion to the water to form carbonate ions. Okay, so in this case here it acts as an acid, or because it has a negative charge and hydrogen here is polar, has a partial positive charge, it can grab a proton from the water to form carbonic acid. Okay, and then so this, in this case here, it acts as a Bronte-Lowry base because it's a proton acceptor. Okay, now which of these two reactions actually will take place in solution? We have to look at something else. We have to look at the equilibrium constant of the acid and the base reaction, and at this point here we're not going to go into it. If you go on and take Chem 401, we're going to go into it, but not at this point. Okay, so here I'm just using this example to as example of amphiprotic substance. Now you cannot have a solution that has hydrogen carbonate. Okay, this reaction between carbonic acid and bicarbonate ion, this is at equilibrium. Okay, and now how are you going to have a reaction something like this? Okay, so this one here, for example, if you take a sodium bicarbonate solid, okay, so it has hydrogen carbonate ions in there, it's a polyatomic ions. So if you take a handful of that solid and you drop into a beaker of water and you stir it up, it will go in solution. When it goes in solution, we can write it as AQ, which means that it has dissolved, and it will dissociate completely to produce sodium and hydrogen carbonate. And when it dissociates completely, then that's the source of the hydrogen carbonate ions, which can undergo either of these two reactions. Okay, so therefore sodium bicarbonate is a neutral compound, but it's an ionic compound, so all ionic compound has a cation and the anions. In this case here, you have to look at the acid-base nature of the ions. Okay, sodium doesn't do anything, but hydrogen carbonate is an amphiprotic substance. It is a conjugate base of the carbonic acid, so it can undergo, it can donate another proton or accept another proton. So it's an amphiprotic substance. Okay, so on the exam, if I ask you, okay, which of the following substance is an amphiprotic, I'm not going to give you something like this with an ions like this, but I'm going to give you a neutral compound, something like this. And then, so you have to recognize that when in solution, when it dissolves, it produces sodium ions and hydrogen carbonate ions, and then you must recognize that hydrogen carbonate is an amphiprotic form of carbonic acid. Another example is the phosphoric acid, which is a weak acid. And how do you know it's a weak acid? Because it's not on the list of the 6 strong acids that you're supposed to memorize. Okay, so phosphoric acid can dissociate and it can produce a first proton to form dihydrogen phosphate. Okay, and then the dihydrogen phosphate can undergo another dissociation and give up another proton to the solution, or release another proton to solution to form hydrogen, monohydrogen phosphate. Okay, so now, for example, and it can undergo another dissociation to release that third proton to the solution. Okay, but let me just stop here now and just because I just want to show you what an amphiprotic substance is. Either dihydrogen phosphate or hydrogen or monohydrogen phosphate are amphiprotic forms, because for example, the monohydrogen phosphate can donate the remaining proton to the water. So in this case here, the monohydrogen phosphate acts as a brontoslurry acid, but it can grab a proton from the water because it has negative charge and to form dihydrogen phosphate. So in this case, and produce hydroxide. So in this case here, it acts as a brontoslurry base because it is a proton acceptor. Okay. And then so again, at this point, we don't know which one is going to react predominantly. And again, if you go on to Chem 401, next semester you'll learn everything about it. But here's the monohydrogen phosphate as an amphiprotic substance. Again, you cannot have a solution that has just a negative ion. Thermodynamically, that's not possible. Any negative ions in aqueous solution has to be balanced by a positive cations. So for example, if you have sodium monohydrogen phosphate solid, which you can buy as a chemical, and then you take a handful of that, put that into a beaker of water that has a water. When it dissolves, it produces sodium monohydrogen phosphate aqueous, and then it dissociates to give you 2 sodium ions and a monohydrogen phosphate ions. And this species here is amphiprotic species because potentially it can undergo these 2 reactions, in which one is acting as a brontoslurry acid, the other one as brontoslurry base. Okay, so but again, it comes as a neutral compounds. Okay, so when you have to consider, a substance whether it's amphiprotic or not by looking at the anions that it produces, and the anion could be a polyprotic anions. Okay. Okay, so here phosphoric acid release the first proton to the solution to produce dihydrogen phosphate. Dihydrogen phosphate can act as a brontoslurry acid by releasing another proton to solution, so it's proton donor, or you can grab a proton from water, so here it acts as a brontoslurry base. Okay, so therefore the H2PO4 minus or dihydrogen phosphate ion is an amphiprotic substance. Now the question is, can phosphoric acid act as an amphiprotic substance? We know, so to be an amphiprotic substance, you have to donate a proton and you have to be able to accept a proton. Obviously, phosphoric acid can donate a proton to the solution, right, or to the water. But to be amphiprotic, it must be able to accept a proton also. And so, which means that if it accepts a proton, it grabs a proton from the water to form, instead of H3, that becomes H4PO4 because the proton is positively charged. So it has to be able to form this species in order to act as a amphiprotic, but this reaction will never occur. Okay, that's not going to happen at all. So therefore, can phosphoric acid be or can a neutral acid be an amphiprotic acid or substance? And the answer is no. Okay, a neutral acid can never be a amphiprotic substance because it can donate a proton, but it cannot accept a proton because it's already neutral. It must have a negative charge in order to do that.